So first thing we're going to start with is nice and easy, just limits in general. So first reminder is when you're doing limits, what's the first thing you always need to do? Plug it in first, right? Always, 100% of the time, just take it and plug it in. Yes, I've yelled at you all enough times about that. I hope just plug it in first. You got something stupid and easy like the limit as x approaches 2 of x plus 7 over x minus 3 or whatever. You know, you just plug it in, right? You get 9 over negative 1. And just plug it in. Easy, right? Anytime you get a limit, plug it in, see what you get. The first two indeterminate forms that we might worry about, right? When you plug it in, you get something like 0 over 0, or you get infinity over infinity. We'll worry about the other indeterminate forms in a bit. But when we get these two are good candidates for us to use L'Hopital's rule on, right? And hopefully everybody, you know, we haven't reviewed our derivatives yet, but if you get 0 over 0 or infinity over infinity, chances are the best option is going to be L'Hopital's rule. Right, which means take the derivative of the top, take the derivative of the bottom, and then reevaluate your limit. So something like the limit as x approaches 2 of x squared minus 4 over x minus 2. Since you plug that in, because that's what you're going to do first, you end up with 0 over 0. You take your derivative. You will indicate on the AP test that you used L'Hopital's rule, because otherwise they will not give you credit for doing it. You will take your derivatives and you will plug it in and get 4 for this particular one. Everybody good with that? Whether it's 0 over 0, infinity over infinity, either way. Take the derivative of the top, the derivative of the bottom. Don't do something like using the quotient rule to take your derivative. Take the derivative of the top, the derivative of the bottom. You can also deal with these by factoring. Right? You can factor this into x plus 2x minus 2 and cancel. You can also sometimes, not in this case, but sometimes do a u substitution to get rid of the 0 over 0 or the infinity over infinity. Common one for that is something like the limit as x approaches infinity of x sine 1 over x. They like to throw this one on there. And this is another different form of indeterminate, right? This is one of the other forms that we talked about this year. This is infinity times 0, which is indeterminate. And you can do one of two things here. One is you can just do a u sub for u equals 1 over x. And if you do that, you're going to get as x approaches infinity, u is going to approach 0. So you can rewrite this limit as the limit as u approaches 0 of the sine of u. And then x becomes 1 over u. So sine of u times 1 over u is sine of u over u, which obviously is still 0 over 0, but we know that limit to be 1. If you encounter this one on the AP test, you don't need to show using L'Hopital's rule if that's equal to 1. You can just indicate that that's equal to 1 because it's a special limit that you should know. Some of the other special ones that you should know, right? Limit as x approaches 0 of x over sine x, also 1. Limit as x approaches 0 of tangent x over x, also 1. Limit as x approaches 0 of x over tangent x, also 1. Limit as x approaches 0 of 1 minus cosine x over x is 0. And same with cosine x minus 1. All of those can pretty easily be done using L'Hopital's rule, but these are just known limits, so you don't need to use L'Hopital's rule on them if you don't want to. Everybody good with that? So that's how the u substitution will work. That's our third form of indeterminate. Good? I'm going to assume that's good. Good. All right, perfect. Next thing to think about with these limits, we didn't really talk about infinity over infinity. Those come up in two different ways. So something like the limit as x approaches 0 of e to the x over x squared, right? This, not x approaches infinity, of e to the x over x squared, right? This is infinity over infinity. So this is a L'Hopital's rule one, if we wish. So you indicate that on the AP test. you'd say e to the x over 2x, and you'd say, oh, that's still infinity over infinity, remembering that you can apply L'Hopital's rule as many times as you need to. So you get e to the x over 2, which is infinity over 2, or infinity. But we might not need to do all that. We might just, if we're sitting there on a multiple choice question, recognize that the numerator is going to increase more rapidly than the denominator is going to increase, and thus the numerator will be getting to infinity more quickly than the denominator will, so the thing will be going towards infinity overall. If the denominator is increasing more quickly than the numerator is, then we know that it's going to be approaching 0. So if we add x squared over e to the x, rather than writing out L'Hopital's rule a couple of times, we can just say this is 0 because the denominator increases more rapidly than the numerator. And just for your remembrance here, the fastest growing functions are what functions that we've dealt with this year? Yeah, factorial now. We didn't have those last year, right? Factorial. And then we have exponential. And then we deal with polynomial growth. Obviously x to the 5th grows faster than x cubed and so on. Down to linear, which of course is also polynomial, but linear. And then we have our root functions, and then we have our logarithmic functions. These all go towards infinity as x goes towards infinity. But in descending order here of speed at which they increase. Everybody good there? Okay. Another thing to think about is something like a limit as x approaches, let's say limit as x approaches pi over 2 from the left of tangent x over 1 plus secant x. And sometimes people have difficulty evaluating these limits with the trig functions approaching like a value like pi over 2. And so we would note here that if we were to plug in pi over 2, well, the tangent of pi over 2, that's approaching an asymptote. We say that the tangent of pi over 2 is actually undefined, right? But it's approaching a vertical asymptote. So this is really infinity over 1 plus, and then once again, it's going to be infinity, right? Same with secant, right? Because these are sine over cosine, and this is 1 over cosine, and cosine of pi over 2 is 0. And so those are going very, very close to 0 in the denominator, so getting very large. So this is another case where we might end up using L'Hopital's rule. That doesn't come up as often, but good to just see it and think about it again. So you'll take your derivatives, you'll indicate that you're using L'Hopital's rule. Secant squared, 1 goes away, secant x tangent x, and that's going to give us a limit as x approaches pi over 2. From the left, we'll cancel the secants, so we get secant x over tangent x, which is 1 over cosine over sine over cosine. And always check and make sure if you can simplify these things down into something easier, that's going to make your life a lot better. Because if you don't do that, you're going to get into such an infinite loop here. The derivative of secant is secant tangent, and the derivative of tangent is secant squared. And you'll cancel, and you'll end up instead with tangent over secant the next time. And you'll do it again, and it'll flip, and you'll do it again, and it'll flip. So make sure that you simplify your trig expressions if you need to in there. So that becomes 1 over sine. So this becomes the limit as x approaches pi over 2 from the left of cosecant of x. And what's the cosecant of x at pi over 2? Should be, y'all should know those values. Oh, good. You guys do know those values. Should be 1. Good? Feeling all right about that? Okay. Cool. Next thing with limits that is sort of important here is you might in the multiple choice encounter a limit like this. The limit as x approaches 0 of something like sine cubed 4x over 3x cubed. And you'd plug in your 0, and you'd see that this is 0 over 0, and you'd say, all right, cool, L'Hopital's rule, right? So then you take your derivative of sine cubed 4x, and you get 3 sine squared 4x times cosine of 4x times 4 over 9x squared. And you plug it in, and you're going to get 0 over 0 again. And you're going to say, that sucks. Now I got to take a derivative of that thing in the numerator again. That's going to be awful. And then you're going to have to do it again, and that's still going to be awful. And then, let's see, you'll have to do it one more time, I think, and that's going to be even more awful. You don't want to have to do that. So we want to remember that we have some of those rules for limits where we can, first off, pull that 3 that's in the denominator out, and then rewrite this as 1/3 the limit as x approaches 0 of sine of 4x over x, all being cubed, and recognize that if I can get this argument inside of the limit here, that's inside of this cubed also to be sine of u over u, by putting a 4 in here and a 4 in here, I should be able to evaluate that limit very easily. So I'll put the 4 in the denominator, the 4 in the numerator, pull the 4 out, which when you pull it out becomes a 4 cubed. And you end up with 4 cubed times the limit as x approaches 0 of sine 4x over 4x cubed. And we'll recognize that we can, in fact, I'll do it right now, we can pull that cubed outside of the limit as one of our rules. So this ends up being 64/3 times 1 cubed, or just 64/3. And so that's going to be much easier than trying to go through and use L'Hopital's rule a bunch of times on that. Everybody remember doing that way, way, way back at the beginning of the year? I hope so. Okay. Cool. Like I said, if you get along the way, if you have questions, just let me know and we'll deal with them. But y'all are doing okay so far? Feel like you probably should be. There, nothing's too bad yet. Cool. So next thing, let's see here. Next thing that we'll talk about is just graphically our limits a little bit. So they do like to put on graphs even on the BC test and then ask you about limits. So just to make sure we're good with all of this, I'm going to sketch a couple graphs and we'll take a look at them. So suppose I have something like this. Let's see here. What else do I want here? That to be an open circle. That an open circle. Let's say that an open circle. Let's do that. And let's put a point in right here. And so let's call this, let's see, let's call this 1, let's call this 2, let's call this 3. That'll be -1. This will be -2. This will be 1. This will be 2. Ignore that the scale is atrocious. Okay. And we'll say that's going forever to the left. So first thing is, I don't know, for some reason, I've always found that people, for some reason, don't like these points where there's like a local minimum or something. So we should note that the limit as x approaches -2 of our function is 0, right? I mean, that's just 0. Just because there's a minimum there, sometimes, I don't know why, but sometimes people screw that up. There's still a limit there just because there's a local minimum, or even if it looks like a corner or a cusp or something, there's still a limit there. It's 0. What about the limit as x approaches -1 from the left? So as we approach -1 from the left, we should be going towards a value of 2, right? So that should be pretty easy, I hope. Yeah? What about as we approach -1 from the right? Should be 0. And that would tell us that the limit as x approaches -1 of f of x does not exist. Everybody good there? In order for a two-sided limit to exist, both the limit from the left and the limit from the right have to equal each other. Yeah? Everybody good there? What about the limit as x approaches 1 of f of x? We have a gap there, we have a hole there, right? But just because we have a hole there does not mean that we are not approaching the same value from the left or right, or even approaching a value at all. So from the left, we're approaching 0. From the right, we are approaching 0. So the two-sided limit must be 0. Right? It's an if and only if statement, right? If and only if the limit from the left and the limit from the right are equal, then the two-sided limit exists and is the same. Even if I put like a point up here, let's say at 3, the limit is still 0, right? We're good with that. It's not what value our function obtains there, it's what value our function is approaching. And then the same thing with at 2, the limit as x approaches 2 from the left ought to be 0. And the limit as x approaches 2 from the right ought to be 3. And therefore, the two-sided limit does not exist and has nothing to do with this extra point that I've thrown in there. We all good there? I hope. Any issues? All right. Let's see. Next thing that we should think about with limits is our other indeterminate forms. So our other indeterminate forms for limits that we needed to deal with this year were, let's see, what do we have? We have 1 to the infinity. We dealt with 0 to the 0, I believe, and we dealt with infinity to the 0. So, and we dealt with some other ones. We dealt with one more also. And we dealt with infinity minus infinity, which we'll talk about in a minute, but that doesn't apply to these. So these ones, 1 to the infinity, 0 to the 0, and infinity to the 0, these are all also indeterminate. And what is the method for evaluating these limits? Suppose I asked you about the limit as x approaches 0 from the right of x to the x power. Right, natural log, exactly. So we're going to take the natural log of this first. So we're going to look at the limit as x approaches 0 from the right of the natural log of x to the x, which is going to give us, not that this is the same, we're going to say look at this limit. So if you had to do this in the free response, you'd want to indicate that this is not equal to this. You're just looking at this other limit to help you investigate the limit you're looking for. So don't put like an equal sign between there. Just be extra careful with notation when you're writing stuff out. So limit as x approaches 0 from the right of natural log of x to the x allows us to take the exponent, that x that's in the exponent, and pull it out to the front. So that allows us to make this the limit as x approaches 0 from the right of x, ln x, which now when we plug that in, we know that this is 0 for the x and negative infinity for the natural log of x, right? Because the natural log function, as you approach 0 from the right, goes down to negative infinity. So this is another indeterminate form, right, that we've dealt with, 0 times infinity. Let me see, hold on a second. Okay, I said looking in 6 equals e raised to the, yeah, that's fine. Yeah, you can write it out with the e raised to the ln of it. That's fine too. Either way you want to do it is good. So Kevin was asking, could you just write this as e to the ln of x to the x, which is the same, and then you can manipulate it in that way, and that's fine too. But
no, I mean like writing the e outside of the limit.
Right. Yeah. That. Yeah. I wrote it there, but it should be there. E to
so that's fine.
Yeah, that's totally fine.
Okay.
They'd be fine with that. Yep. Either way you want to do it. Okay, yeah, so we had 0 times the negative infinity, which we said is indeterminate. And so we can try to figure out how to deal with that, which should be pretty straightforward. We're just going to write this as the limit as x approaches 0 from the right of ln x, and then instead of times x, we're going to divide by 1 over x. Which then gives us a infinity over an infinity, which means we can use L'Hopital's rule, which you will indicate once again that you're using L'Hopital's rule. Don't forget to do that. And you'll end up with the limit as x approaches 0 from the right of 1 over x over negative 1 over x squared. And so when you do that, you'll simplify this down and say this is the limit as x approaches 0 from the right, once again, of negative x squared over x, which is just negative x, which is 0. And so in the end, you'll say, so our limit e to the 0, which equals 1. And, you know, in looking through student responses over the years, on the rare occasions that they throw this one up on in a free response where there's an indeterminate limit that's like one of these indeterminate forms, I've seen quite a few student responses where they do everything perfectly and then forget to go back at the end and exponentiate their answer. So don't forget to go back and exponentiate your answer at the end. Yeah? Everybody good there with that? Wonderful. All right, and then the last indeterminate form that we talked about was infinity minus infinity. What's a good problem? I don't have one off the top of my head for this one because I forgot about this one until a second ago. Infinity minus infinity. Let's say something like, give me a second here. I'll come up with something good. All right, sure, that works. Okay. Kevin sent me one here. That's good. Limit is what we would get. X approaches 0. We're gonna have to make it 0 from the right of 1 over x plus ln x. So if we look at that, that's going to end up, as we approach 0 from the right of 1 over x, that's going to be infinity. And as we approach 0 from the right of ln x, that's going to be infinity or negative infinity. So we're going to have an infinity minus an infinity here. And so there's another indeterminate form. And so the method that we want to use to deal with these is we want to be able to combine them together into a singular fraction. So we're going to get ourselves a common denominator here to do this. So that'll be x over x here. And so we'll end up with 1 plus x ln x over x. And we'll note that if we try to deal with, let's see, if we try to deal with this one, the limit as x approaches 0 from the, we'd have to look individually at the x ln x part. Yeah, that's still going to come out to be 0 over 0. And so, well, it's going to come out to be 0 times infinity. But if we rewrote the x ln x part as ln x over 1 over x, that's a 0 over 0, which, what does that limit come out to be itself? Probably, hopefully, negative 1. Let's see here. Limit as x approaches 0 from the right of ln x over 1 over x. That's 1. We just did that one, didn't we? Yeah, that came out to be, no, that just comes out to be 1, right? Yeah, we just did that one a second ago. Is that right? Now I gotta write it out. Did we just do that one? I didn't want to write it out, but x ln x. Maybe we did. Okay, limit as x approaches 0 from the right of x. Well, it's 1 over x with an ln x above it. That gives us an infinity over infinity. So it's 1 over x over negative 1 over x squared. Yeah, okay, that's negative 1. Yeah, okay. Or no, that's 0. That's 0. Negative x squared over x, which gives you 0. So this ends up being 1 plus 0 over the 0 there. Which tells us that this thing should be going towards infinity. So combine them together. If you don't get something that's indeterminate, then deal with it that way. If you do get something that's indeterminate, then you might have to use L'Hopital's rule to deal with it after that, or what have you. Everybody good with that. Okay. All right. Let's see. So that, I believe, is the majority of the stuff that we did just regularly with limits. Then we took our limits and we started to look at them in terms of the difference quotient, right? We said, let's look at the limit as h approaches 0 of f of x plus h minus f of x all over h. And we said that this is the, I should write that more clearly. This is the, I tried to write it more clearly, the limit definition of the derivative, right? And we talk about derivatives as the derivative, right? We know is the slope of the tangent line to the curve at a point, or we even call it the slope of the function. It's the instantaneous rate of change of the function. Any of those things are fine. Those are all the same. This is one form of the limit definition of the derivative. The other form of the limit definition of the derivative that you should be familiar with, because it does pop up on occasion in the multiple choice, is the limit as x approaches a of f of x minus f of a all over x minus a. And so sometimes in the multiple choice, they may give you some limit that's like, all right, something like the limit as h approaches 0 of f of, well, they won't say f of, they'll say like, let's say sine of pi over 4 plus h minus root 2 over 2 all over h. And so what they're expecting that you do here is they're expecting you to look at this and say, all right, well, this is the limit as h approaches 0 of f of some x value plus h minus f of sine of that same x value, right? Sine of pi over 4 is root 2 over 2. And so they're expecting you to recognize that this is the limit definition of the derivative and that this is just the derivative of sine of x evaluated at x equals pi over 4, right? In other words, it's cosine of pi over 4, or just also root 2 over 2. You may see the same thing using this form of the limit definition of the derivative. It's okay if you don't recognize that. It's not the end of the world, because when you plug in 0 for h here, what do you get? You get sine of pi over 4, which is root 2 over 2, minus root 2 over 2, which is 0 over 0. You can just take the derivative, and that's effectively going to do the exact same thing, right? If we take the derivative using L'Hopital's rule, we're going to get the limit as h approaches 0 of the cosine of pi over 4 plus h all over 1. And as h goes towards 0, that's just the cosine of pi over 4, which is just root 2 over 2. Everybody good with that? So those often pop up that way. Okay, cool. All right. Limits. I'm pretty sure anybody think of anything they want me to talk about with limits? I think that's everything. We'll talk about limits with improper integrals and all that stuff later, but I think that's good. Everyone good? Squeeze theorem. Okay, yeah. The squeeze theorem and sandwich theorem only pops up every once in a while. In fact, I've only seen it like once in the last few years. My guess is, we used it a few times to look at something like the limit as x approaches 0 of x squared sine of 1 over x squared, which, we had difficulty dealing with in any other way, except we needed to find a function that was always greater than or equal to this and a function that was always less than or equal to this. And so the way that we went about this is we said that the sine of 1 over x squared is always less than or equal to 1, greater than or equal to -1. And so we just multiply both sides by the x squared. And then we do a limit as x approaches 0 of negative x squared, which is 0, and a limit as x approaches 0 of positive x squared, which is also 0. And so by the squeeze theorem, since we know that x squared is always greater than or equal to x squared sine 1 over x squared, and negative x squared is always less than or equal to it, and the limits of both of those as we approach 0 are 0, by the squeeze theorem, that tells us that the limit as x approaches 0 of x squared sine of 1 over x squared also equals 0. And generally, they might just, I mean, I doubt they'd give you one like this. If they did, it'd probably be in the multiple choice. I think that's just a little too easy for them to throw into something in the free response anyway, but they might throw something in where they just make some blanket statement that, you know, that some function f of x is always greater than g of x, and that h of x is always less than or equal to that same function. And then they might have you find the limits. So, like, you know, maybe they say that maybe in the multiple choice they say like the limit as x approaches 7 of f of x is what you're looking for, and they say that f of x is always less than or equal to g of x greater than or equal to h of x, and they say that h of x is equal to, I don't even know, whatever, something like the square root of x plus 2, and g of x is equal to, I mean, these functions may not work for that, but that's fine, 2x minus 2x minus 11. What's the limit is x approaches 7 of f of x, and you'd say, well, since I know that f is sandwiched between g and h, and I can find the limit of h as we approach 7 to be 3, and I can find this one to also be 3, then therefore this one must also be 3. So you might see something like that, where they don't give you the function f of x, but they give you some other functions that surround it. Obviously, these functions, I mean, these don't necessarily match up. I just thinking of something off the top of my head to make them equal. This is not really probably true, but does that make sense conceptually? What they might show in the multiple choice, what type of problem they might give you for that? I've seen one or two of those over the years, not very often, but cool. Let's see, limits. Yeah, I'm gonna get into all the theorems here in just a second. Yeah, we'll talk about the intermediate value theorem. So intermediate value theorem, we should recognize that one pretty easily. Just to make sure that if you're in the free response and you're trying to note using one of these theorems, that you always make a point about the initial condition. So intermediate value theorem tells us that f of x is continuous on A to B. Right, so if f of x is continuous on A to B, then that tells you that for any value between f of A and f of B, there exists a C on the interval A to B such that f of C is between f of A and f of B. So for any value, I guess I should have said for any value f of C between f of A and f of B, there should be a C on A to B. I sort of restated the whole thing twice there, which is unnecessary, but effectively, you know, we've got some function that's continuous. Here's f of A and here's f of B. Tells me that any value I choose between this f of B value and this f of A value, any y value, so, you know, for example, 0, I know that there's a place between a and b where the function itself equals 0, or effectively equals any value between f of b and f of a, often used to indicate that there is a root on that interval if there's a sign change between f of a and f of b. I doubt that they would ever ask you to like do anything other than use this in the context of a chart in the multiple choice. That's usually how the intermediate value theorem shows up, is that every once in a while it's in a free response given like some chart. They'll be like, all right, why, you know, they'll say something like, here's a chart of values, here's x and here's f of x and g of x even maybe, and they give you some values here and they're like x is 0, x is 2, x is 4, and f of x is 1 and 7 and 10 or something. And they might give you some other values over here that don't even matter, and they'll say, does, you know, if, as we'll say, f is continuous on 0 to 4, and they'll say, does f obtain a value of 3 on the interval 0 to 4, and you'd say yes, because f is a continuous function from 0 to 4, and it goes from 1 to 10 between 0 and 4, and therefore it must hit 3 somewhere between 0 and 4. Might hit it as many times as you want it to, right? You could hit it 17 times in between there. It doesn't really matter, but that's usually what you'll see is, and you'll explain, you'll say, well, yeah, it's because of the intermediate value theorem. F of 0 is 1, f of 4 is 10, therefore f of x must equal 3 on the interval between 0 to 4 by the intermediate value theorem. Easy enough? Cool. All right. Now, as far as derivatives, I'm not going to go through all of the rules for derivatives, all the basic rules, because I think that's just a waste of everybody's time. I think you all should know how to take derivatives of, you know, constants. Derivative of constant is 0, right? Derivative of a linear or polynomial function, you use the power rule. If functions are being multiplied together, use the product rule. If they're divided, use the quotient rule. If it's composition of functions, use the chain rule. If you can't take your derivatives by this point, you've got a lot of work to do before the test in 1 week. So the important thing, though, is that our derivatives are the slope of the function, they are the instantaneous rate of change of the function, and they are the slope of the tangent line to the function. So oftentimes, of course, they're going to ask you to write the equation of the slope, or write the equation of the tangent line to a function at a certain point. So anytime they ask you to do that, if you're asked to write the equation of the tangent line, just find yourself a point. They'll at least give you an x value, right? So you can find the y value by plugging it in, find your slope by using your derivative. And my suggestion is always just put it into point slope form. That's why you have a point and a slope, is to put into point slope form. They will never ask you, I've never seen them ask you to put something into another form. They don't ever say put it in standard form, put it in slope intercept form. They don't care. Put it in point slope form. Don't bother with the extra arithmetic and the algebra, because if somehow, even though you're all very bright individuals, if you somehow make a stupid algebra mistake, you're going to lose some points on it. So you don't want to do that. So just put it straight into here. Now, we talk about tangent lines in terms, well, actually, let's go a little further with derivatives before we start talking about the tangent lines. I want to talk more about tangent lines in a bit, and when we use them to approximate functions and what that means. But first off, let's just talk about the idea of the derivative. So f prime, if f prime is positive, we know that our function is increasing. That should be easy. If f prime is negative, it tells us that our function is decreasing. Much to my chagrin, use brackets on increasing and decreasing intervals, except at infinity or negative infinity. Okay? That's just the way that they want it, right? So if the derivative is positive, it increases. If the derivative is negative, the function decreases. I should say f is increasing, f is decreasing. We can take our second derivative, right? Take the second derivative of any function easily enough by just taking the derivative of the derivative. F double prime greater than 0 tells us that it is concave up. F is concave up. F double prime less than 0 tells us that F is concave down. We were concave up, concave down. And we'll remember that we can find points that are local maxima and local minima by looking for when the derivative is 0 or when the derivative is undefined, right? So, and I want to just make a note about a couple things about that. A local min or a max is possible if f prime equals 0 or f prime is undefined. These are called critical values, right? Those are critical values, places where the derivative is 0, where the derivative is undefined. But you must prove it, so use a sign chart to check. Or if f prime is 0, you can use the second derivative test. So we'll quickly just mention what is the second derivative test. The second derivative test says that if the derivative is 0 at a point, let's just say, for example, y equals x squared, right? Well, actually, let's use what do I want to use here? Let's use y equals x to the 4th minus x squared. So if we take the derivative of this, we get y prime equals 4x cubed minus 2x. This has two places where it might have, or actually 3 places where it might have a local max or a local min. We're going to take a 2x out of this, giving us 2x squared minus 1, giving us x equals 0 and x equals positive or negative square root of a half. I'm just going to specifically use x equals 0 because that's just easy. So the second derivative test tells us we can look at y double prime of 0. So y double prime should be 12x squared minus 2. And if we evaluate that at 0, we get negative 2. And so since the second derivative is negative, that tells us that the function itself is concave down surrounding that on that interval at that point. And if it's concave down, that's how we end up with a max. And if the function happened to be concave up, if the second derivative was positive at that value, then we'd have a local min. Everybody remember that with the second derivative test? All good, y'all still there? All right. Cool. So let's see, first derivative test. So you can use a sign chart to check, or you can use a second derivative test. Same thing, we can find points of inflection, right? So points of inflection is possible if f double prime equals 0 or f double prime is undefined. And then you need to use a sign chart on this one to see a sign chart with your second derivative to see if the actual concavity of the function changes. You need to check for the change in concavity on a sign chart. If you don't check, they're not going to give you the points on a free response, right? For indicating a point of inflection if you haven't proven that there is one there. All right. Now, I want to go back to talking about tangent lines. So when we talk about tangent lines, we think about a function that is concave up. So let's say we have a concave up function on some interval, and we've used a tangent line on that interval to approximate the value of the function near where that tangent line hits. So our tangent line hit it, let's say, at 1. We wanted to approximate at 2. If the function is concave up, that tells us that the tangent line is always an underestimate. If you forget that, it's really easy to just sketch the graph. Sketch something that's concave up, sketch a tangent line to it. You will see that everywhere else, that value from the tangent line is less than the value from the actual function. Right, so the tangent line is an underestimate of the true value. If your function is concave down, the opposite of that is true, right? If it's concave down, your tangent line is an overestimate of the true value. And this comes up fairly often in the free response, right? Oftentimes in differential equation free response questions, particularly, where they'll give you, they'll give you dy dx, and then you'll have to find the second derivative, and then you'll have to determine if it's an under or an overestimate of the true value. Sometimes they may even talk about a secant line. Okay, so I get a secant line on a concave up function. The secant line on the interval between A and B, where your secant line hits your function, any value there should be an overestimate. And here a secant line should underestimate if concave down. And those are all things that are relatively commonly asked on the AP test. Everybody good there with those? Cool. All right, let's see here. So derivatives. We're not going to go through all the rules for the derivatives. Let's talk quickly about derivatives of parametric functions. So any parametric function that you've got x of t, y of t, right? Or just x equals f of t, y equals g of t, let's say, how we want to write it. If you want to find the slope of the tangent line, if you want to find dy dx, just remember that it's always dy dt over dx dt. Right? So for any parametric, dy dx is dy dt over dx dt. If we want to find the second derivative, then we have to take our first derivative. So we have to find dy dx, and we have to take the derivative with respect to t of dy dx, which will be easy enough because dy dx will be all in terms of t. And then you need to divide it by dx dt. And that, I'm not going to go through the whole proof of that again. We did it back in class, but that's because of the chain rule, because you're taking the derivative with respect to x of something in terms of t. So when you do that, you have to multiply it by the derivative of t with respect to x, which is dt over dx, but multiplying by dt dx is the same as dividing by dx dt. And so that's what we divide by, the dx dt. And so that should give you a second derivative of a parametric function. Remember that we can find a max and a min by just investigating the max and min of the y function, and we can find a rightmost and a leftmost point by investigating the max and min of the x function. So use dx dt to find leftmost and rightmost, and use dy dt to find max or min. Everybody good there? Perfect. All right, let's see here. What else do we want to talk about? We talked about polar functions, right? That'd be good. So polar functions, right? We get r equals f of theta, r equals something in terms of theta. We want to find the slope of the tangent line to that. Dy dx ought to just be dy d theta over dx d theta. In order to find the y and x, y is always equal to, what is y always equal to?
R sine theta.
Should be r sine theta, good. X should be r cosine theta. And so we'll just take our r value, our f of theta, multiplied by sine, multiplied by cosine, take the derivatives of those with respect to theta to get your dy dx there. All good with that? Any questions or issues with that? Okay. I want to go back a second because I just happened to think of something. The extreme value theorem. I didn't mention this one. We talked about this way back a long time ago for just like 2 seconds. Back in like September. The extreme value theorem says that if f of x is continuous on A to B, then it can, we'll say then it has an absolute max and min on that interval, guaranteed 100% of the time. And so I'm going to touch on this again a little bit in a second, that if you are looking for an absolute max or a min and you are given a closed interval, you need to check your endpoints. Don't forget to check your endpoints. That is a common mistake in the free response questions, especially in like some of those rate type questions that we've done in the past. If you were in quarter 1 and 3, if you're quarter 2 and 4, we haven't done them yet, but we'll be doing them very soon. So in these rate type questions, they will often ask about an absolute max or an absolute min. Make sure that you check the endpoints if the interval you are given is a closed interval. If the interval you are given is not a closed interval, if they give you an open interval, then don't check the endpoints because there are no endpoints to check. And every once in a while, they'll throw a question on that's they're trying to just see if you remember the initial conditions of these things, where they'll say that something like, they'll say like f is defined on the closed interval from A to B, but it doesn't have an absolute max or a min on that interval, or it doesn't have an absolute max on the interval. How could this be? And they'll give you a list of reasons, right? Well, just because it's defined from A to B doesn't mean that it is continuous from A to B. If it's not continuous, then it doesn't have to have an absolute max or a min, right? I could sketch something real easily like this. This is defined from A to B, but it is not continuous on the closed interval from A to B. Therefore, it does not have to have an absolute max or an absolute min. And in this case, it does not have either, right? We're getting very, very close to 0. We're getting very, very close to whatever this value is, but we never get to 0. We never get to whatever that y value is. But it's still defined in all the values because I filled in the gaps at A and B by plugging in some points there. Does that make sense to everyone? Okay. And then the other thing I wanted to talk about, I forgot to when we were talking about limits, is the idea of continuity, right? So sometimes they will ask you if something is continuous at a specific point. So if we want something to be continuous at C, let's say, if something's going to be continuous at a point x equals C, 3 criteria must be met. The first is that f must be defined at C. The second is that the limit as x approaches C of f must exist. And the third is that f of C must equal the limit as x approaches C of f of x. Right? And that's the definition of continuity. If the limit exists, the function exists, and the limit and the function are equal to each other. The function is then defined at that, or the function is then continuous at that point. And if they ever ask you to prove that something is continuous at a point, you must show all 3 pieces of that to prove that something is continuous at a point. And this often pops up in multiple choice questions where they'll give you like a piecewise defined function. They'll say something like f of x is equal to x squared minus 1. We'll say it's equal to I don't know, we'll just say, how about 2x plus 3. We'll say if x is less than or equal to 3, if x is greater than 3, they'll say, is this function continuous at x equals 3? And so you'll say, well, is it defined at 3? F of 3. F of 3 is, let's see, it looks like that's 8, right? Or we would then say the limit as x approaches 3, and you'd have to then look at the left and the right. So the limit as x approaches 3 from the left of f is 8, and the limit as x approaches 3 from the right of f is 9. Therefore, second criteria isn't met. The limit as x approaches 3 of f does not exist, therefore not continuous. Right? Easy enough. Okay. Sometimes, and I'm gonna let's adjust this problem ever so slightly. Let's say that the limit, let's just say that f of x is equal to, what did I just have here? X squared minus 1 if x is less than or equal to 3, and then 2x plus 3. Right? So let's just do 2x plus 2 if x is greater than 3. And let's determine, is f differentiable at x equals 3? Well, for it to be differentiable at x equals 3, the first thing you need to check is it continuous? So if back here, if I'd said, is it differentiable? Well, then you'd look and see that it's not continuous and say, no, it's not differentiable because it's not continuous. Remembering that, and we'll come back to this problem that I just started in a second, remembering that there are 4 criteria for why a function is not differentiable at a point. What are those 4 criteria? 1 is that it has a discontinuity. 2 is that it has what? A corner. 3 is that it has a cusp. And 4 is that it has a vertical tangent line. So 4 reasons why a function might not be differentiable. So in this one, if I asked if it was differentiable, no, because the function is not continuous. Here, we'd go through, and first we'd see, is the function continuous at 3? Well, we'd say the limit as x approaches 3 from the left is 8. Okay. The limit as x approaches 3 from the right of f is 8. So therefore, it must be continuous at 3. So that gives us a chance. But then we need to look at the derivatives from the left and from the right. So we'll say f prime equals 2x if x is less than or equal to 3. And we'll say f prime is equal to 2 if x is greater than 3. Well, at 3, this would be 6 versus over here, this would be 2. So it would not be differentiable in this case either. But if those come out to be the same, then it would be. Good or no? We need to do anything else like that, or we all feel okay about that? All good? All right. Let's see here. So going back, what was the last time we talked about derivatives before we moved over to parametric? This tangent line stuff. Okay. So another thing to remember here about your derivatives is the idea of linearization, right? And you want to remember the linearization formula. L of x is always equal to f of a plus f prime of a times x minus a. This is to approximate f of x at a value very close to a, where we know what f of a is. F of a is a known value that's easy for us to figure out. Right, so where I might say, like, what's the approximate the square root of 50, right? Well, then f of x would be square root x. A would be 49, because we know the square root of 49, and the x value that we're using would be 50. So L of 50 would be approximately f of 50, right? F of 50 is approximately L of 50, which would be the square root, our f of x function, of 49, plus 1 over 2 root 49, because that's 1 over 2 root x for the derivative of root x, and then times our x value minus our a value. So we'd end up with 7 and 1/14, right? Or whatever that is, 99/14. And that's our basic idea of how linearization works. We only really want to use linearization on small scales where the value that we're looking for is very, very close to a value that we know the actual numeric value for. Good or no? All right. Y'all doing okay? Nobody needs a break or anything. We're good to keep moving? Hopefully. Okay, just making sure. All right. Other things we should talk about involving derivatives include the inverse rule. The inverse rule usually pops up one time in the multiple choice. Remember that the inverse rule says that if f and g are inverses and f contains a point a, b, that means that g must contain the point b, a, and f prime of a is 1 over g prime of b, or vice versa, g prime of b is 1 over f prime of a. So we really just need to know that formula. And I would say a good majority of the time, this shows up in terms of like, they'll just give you a chart with a bunch of values on it and tell you that f and g are inverses, and then ask you to find, f prime of 7 or something like that. And so I don't know, let's make a quick chart, I guess, and do an example of that. So x, f, and g. Let's say we've got, let's say I want to find f prime of 2. Let's see, we got a 1, let's put a 2 in here, let's put a 4 in here. And let's put a 7 in here, just give ourselves a bunch of extra information that we don't need. And let's say, we're also given g prime values here. And we want, what did I say? We want f prime of 2. So let's put some stuff in here. Let's put in a 3. Let's put in a 5. Let's put in a 6 and a -2 here. And let's say that, and that's not put it in. That's not too good. Let's do something like 2, 4, 7, 8. And then let's do 3, 5, 2, 1, and let's do 6, 4, 3, 8. I don't know, something like that. So if we want to find f prime of 2, we know that f must contain a point 2 comma something. Well, that'd be 2 comma 4, which means that g contains a point, hopefully 4 comma 2. If I made my chart right, oh good, I did. And if we want f prime of 2, that ought to just be 1 over g prime of 4. And g prime of 4 is 3, so that ought to just be 1/3. So they'll just give you a chart with a bunch of extra values, and they would have put in, answers of 1/3, 1/6, 1/4, 1/2, a bunch of answers to try and throw you off. And the answer is 1/3. Everybody good with that? All right. Let's see here. What else do we do with derivatives? We talk about the mean value theorem for derivatives, MVT for derivatives. Right, the MVT for derivatives has more than just one piece of initial condition. It has two, right? It says that if f is continuous on A to B and it is differentiable on A to B, then there exists a C on the interval A to B such that f prime of C equals f of B minus f of A over B minus A. So it's telling us that if the function is continuous and differentiable on the interval from A to B, that somewhere on the interval A to B, the average rate of change, that's f of B minus f of A over B minus A, the average rate of change is equal to the instantaneous rate of change. And we're noting that this occurs on the interval A to B. So I got some function that looks, like this. The average rate of change is this, so that slope. There must be somewhere on that interval. Well, that was horrible. There must be somewhere on that interval where the instantaneous, where the slope of the tangent line is equal to the slope of that secant line, right? It's guaranteed that's the case if the function is continuous and differentiable. Doesn't mean that there's only one. Looks like in this case there's a second one right over here, right? But that's there's at least one. Everybody good with that? That will often pop up in charts as well, where they're giving you, we could even go back to this last chart we were looking at. If we said that, we'll talk about, if we talked about the function g of x and we said that g was continuous and differentiable here, and I said, is it true that somewhere on the interval 1 to 2 does g have a slope of 2? And we're going to say g is continuous and g is differentiable. We'll just say for all x. So on the interval 1 to 2, the average rate of change of g is 5 minus 3 over 2 minus 1, which is 2, which tells us that somewhere on the interval from 1 to 2, g prime must equal 2, right? So yeah, that's how that might pop up, something like that. They may even be, they may try to be tricky. They could say something like, is g prime strictly, let's change this value to something like 1. Is g prime strictly decreasing? And it looks like it's 6, 4, 3, 1, but no, it's clearly not strictly decreasing, because we know that somewhere between 1 and 2, the derivative of g must be 2. So it went from 6 to 2 back to 4. So g prime is not strictly decreasing. It'd be something like that. And your explanation, if you had to do it in a free response, would be no, because the mean value theorem for derivatives says that on the interval 1 to 2, the derivative of g must equal the instantaneous rate of change of g, which is 2 on 1 to 2. Does that make sense to everybody? There'd be other ways to prove it using the other values in there, but cool. Everybody still hanging in there, feeling all right? Yeah, look at that. We've made it 74 minutes, a regular class period this year. Okay. So, mean value theorem, intermediate value theorem we did, extreme value theorem we did, and no other. Oh, the only other thing would be they might just use the term Rolle's theorem, and we would just note that Rolle's theorem is just a special case of the mean value theorem, where f of b equals f of a. If f of b equals f of a, that's telling you that the slope is 0. It's telling us that it's a slope of 0. It's telling us that there is a critical value on the interval. right? And so they may use the terminology of rules, theorem, and just remember that that's what that is. That's a special case of the MDT. Cool. All good there? I hope. Okay. You missed calculus class, Darius? Oh, that's good. I wouldn't think that this would make you miss it. This is, I don't know. This is just like, I don't know. My children watch these like video game videos of people doing like video games as fast as they can. They call them, what do they call them? What do they call them? Speed runs. This is like a speed run of AP Calc. The AP Calc speed run. How fast can we get through everything? And now I'm rambling about that for 30 seconds, and now we're behind. Okay. Other things we should talk about with derivatives is if we're given a position function, right? The derivative of position. We'll call this position. This should be easy. Derivative of position is velocity. The derivative of velocity is acceleration. Derivative of acceleration is jerk, and so on. You're not going to need to know anything beyond the derivative of velocity is acceleration. Be extra careful in any motion problems that are just like a motion in a line, because you might see one of those rather than vector motion. Speed is the absolute value of velocity. Okay? Speed is the absolute value of velocity. Speed can never be negative. Okay? And we want to note that specifically, if they ask you, is speed increasing? That would mean that velocity and acceleration have the same sign. And if they ask you, if you find that the speed is decreasing, that would mean that velocity and acceleration have different signs. Everybody good with that? And I know we haven't started talking about integrals, but just real quickly here, if you're talking about motion in a line, the integral of velocity, the integral of your velocity should be your displacement, and your integral of speed, usually needing to be done on the calculator because of the absolute value, the integral of speed is the total distance traveled. Everybody good with that? I hope. All good? Okay. So we will, we could go into, we won't worry about the vector stuff quite yet. We'll move back to the vector stuff in a bit. You might see some optimization problems, right? If you think about optimization problems, usually you just see an optimization in the multiple choice, usually. So if you get an optimization problem, just remember that really all you're looking for is you're looking for a max or you're looking for a min. Make sure that you look at the domain of the function that you write, including anything given to you about the like situation. So like if it says that, if it says that we're taking a sheet of paper and cutting off the corners, and it says that this paper is, well, let's call it like 9 by 12. That's a size of paper or something, right? Or a photograph. 9 by 12, and we're cutting off corners that are x units by x units here. Well, we know that the largest value x could be, x is going to be less than 4.5, right? Everybody good with that? So checking in the domain, don't come up with a value that's more than 4.5, and x is obviously got to be greater than 0. That kind of stuff. Good? Okay. In terms of related rate problems, a couple of things to remember about related rates. Number one, you are always taking your derivative with respect to time. Right? Always taking your derivative with respect to time. And remember that you do not plug in values that are changing ever. Well, not ever. You don't plug any values that are changing in until after your derivative. Okay. Don't even label things that are changing on your picture as a number if that value is changing. Okay, label it as a variable and then deal with it. And some of the things that you want to look out for with your related rates, you know, I'm not gonna do a bunch of related rate problems because chances of you seeing more than one in the multiple choice or maybe one in the free response is slim. But just remember that you want to look out for things like similar triangles. Right, similar triangles pop up fairly often. Be careful if they give you trapezoids, because rules for similar trapezoids are not the same as similar triangles. You might need to break it up into like a rectangle and a triangle to deal with it that way. You know, they usually will give you the volume formulas, but if they're talking volume and surface area, and they're usually going to give you the volume and ask you to like maximize the surface area or vice versa. They'll give you an actual value that they want the volume to be. So you'll use that formula to write one variable in terms of the other. Right, one variable in terms of the other and then substitute. Right. So just remember that you need to do that with these related rate problems. Good or no? Everybody still doing okay? What is the word before one? Right. Write one variable in terms of the other and substitute. Good now, Nick? Okay, cool. Let's see here. I'm just going to skip back for a second. Remember that same thing applies here if you're talking about vectors, right? If you have a position vector, the derivative of the position vector is your velocity vector. The derivative of your velocity vector is your acceleration vector. And remember that, and I'll just throw an extra page in here. Remember that when we're talking about vectors, the speed, right, is still the absolute value of velocity, which is the magnitude of your velocity vector. Okay. And so remember that that is the square root of, you know, it's just your Pythagorean theorem. It's your square root of a squared plus b squared. The x component. Yeah, that's good. That's fine. It's just the square root of the x component squared plus the y component squared from your velocity vector, right? Good with that? I guess I'll just velocity. The x component of your velocity and the y component of your velocity. And same things apply. Like if you integrate this, that's going to give you your total distance traveled. If you're looking for the direction of motion, you need to do the inverse tangent of y over x from your velocity vector to get the direction of motion of the particle in a plane when you're talking vectors. All right, let's see, derivatives. Anybody think of anything else with derivatives they'd like me to talk about? I think that is pretty much everything with derivatives, unless somebody has got something off the top of their head that they have a question on. Linearization we did, Nick. Somewhere. Linearization, there it is. Newton's method will not be on the AP test, Kevin, so you don't need to worry about that. Just it's not technically in the curriculum. It's just something I throw in because I think it's cool to see how it works. Anything else, anybody? All right, let's keep moving forward. I don't think we're going to quite get through everything in this 2-hour session here. We may have to take an hour of next week's, not next week's, but next time's to finish up. Let's talk about integrals. We talked about area underneath a curve, first of all. We talked about area underneath a curve. We can approximate the area under the curve, so we'll start with that. You will likely have to approximate area under a curve. And there will be 4 different ways that you'll be expected to approximate the area underneath the curve. One is the left rectangular approximation, one is a right rectangular approximation, one is the midpoint rectangular approximation, and then the trapezoidal rule. Right, so 4 different ways that you'll be expected to approximate the area underneath the curve. I don't think I need to so much really talk about this too much of how to do it, but there's your left rectangulars. You just start at the left pieces of each of your intervals and make rectangles. Your right rectangular approximation, you start at the right side. Right? Your midpoint rectangular approximation, you take, if I have subintervals like this, I take the midpoint of each one, right? And I make my rectangles that way. Right. Obviously, midpoint is more accurate than the left and the right. And then your trapezoidal one, obviously, you make trapezoids out of it, right? So from here to here, make a trapezoid. 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 And that's better than the left and the right as well. Things to note about that is that a left rectangular approximation, if your function is an increasing function, if it's an increasing function, your left will be an underestimate, and you can always sketch it out to see. The left rectangular approximation of a decreasing function will always be an overestimate. Okay. Talking about a right rectangular approximation, it's just the reverse. If that's an increasing function, it's going to be an overestimate. And if it's decreasing, it's going to be underestimate. In terms of the midpoint rectangular approximation, they don't usually ask about that. So you're not going to need to worry about that. But the trapezoidal, they will. And so for a trapezoidal one, and I'm going to sketch a concave down function to note this. A concave down function, right? This is an underestimate, but for a concave up function, it's an overestimate. And, we can see that, right? Here's our axis. Everybody good with that? These trapezoids will extend down and they'll be over the function, and these trapezoids will extend down and they will be under the function. Everybody good with that? I hope. All right. If you have equal subintervals for your trapezoidal rule, you should just be able to go ahead and use the formula, right? So the trapezoidal rule formula with equal subintervals should just be h over 2 times y naught plus 2y1 plus 2y2 plus and so on 2y sub n minus 1 plus y sub n, with h equal to b minus a over n, the length of a single subinterval. Right? But if you do not have equal subintervals, then you've got to go through and you've just got to find the area of each trapezoid individually. Same thing with rectangular. If if you have equal subintervals, you can factor out the length of it and just add all the different values together, and then multiply by the length at the end. But if they are not equal subintervals, you have to find each rectangle separately and approximate it that way. Sound good to everybody?
Yes.
Okay, I don't think we talked about Simpson's rule this year, but if we did, that's not on the AP test, so you don't need to worry about it. So good point, Kevin. You asked if you're showing your work and you said that the trapezoid is the average of the left and the right. Yes, that's totally fine. You can definitely do that, and that is definitely 100% of the time true. So that's fine. The trapezoidal is the average of the left and right rectangular approximations. And let's see what else. I can't think of anything else. Oh yeah, and sometimes they'll give you a chart and ask you to do the midpoint rectangular approximation. If they give you just a chart of values and they ask you to do the midpoint, that's also going to end up being the average of the left and the right. So that works too, but only if they give you just a chart of values and not some smooth curve that you're drawing. Okay, let's see. Next thing we need to be able to do with integrals is we need to be able to take a right Riemann sum and turn it into a definite integral. And this, I would say, over the last 5 years, there's one of these every year in the multiple choice. They don't usually show up in the free response, but it's, that's worth 1.2 points toward your score. So you might as well not miss it. The limit as n approaches infinity of the sum from n equals 1, not n equals 1, k equals 1 to n of the function f of x sub k times delta x. So this is what we need to be able to write out given some definite integral. So they may give you an integral from 2 to 3 of x squared dx. And they may say, write this as the limit of a Riemann sum, or write Riemann sum. And so you would say, okay, well, the delta x comes from our b minus a over n. That's effectively the length of each subinterval. So that would be 3 minus 2 over n, or 1 over n. And then your x sub k is how far over you have gone from the y-axis to go up to draw that first rectangle. And that should always be equal to a plus k delta x. And so in that case, that'd be a 2 plus k times our delta x. So 2 plus k over n. And this should then be the limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k. Well, our f of x is x squared. So that should be x sub k squared, or 2 plus k over n squared, and then times delta x, which is times 1 over n. Chances are this is as far as they will make you go with this. They might, if it's multiple choice, have this distributed out and all distributed together, but that's just algebra that I expect you guys can do without me reviewing that with you. What they're not going to ask you to do, I've never seen them ask, but I make you guys do it anyway, is they're not going to ask you to evaluate it in a free response question using the limit and the summation. If by some chance that happened, the only two that you would need to know is the sum from k equals 1 to n of k is n times n plus 1 over 2, or potentially that the sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 over 6. That is not in the curriculum for this class, though, so I can't imagine that they would, but I always like to teach it because I think it's important. But just because there is some stuff with series in this class that they might throw something like that in. It's not really supposed to be in there. So just be aware of those, but not super important. You shouldn't need to use it. Good with that? Any questions there? You all feel like you could do that? If you know these formulas, you should be pretty good in order to write out that Riemann sum as a limit. Okay, you're all still there? You guys good? Zoom is still going? You're all here? Okay, just making sure. Cool. All right, let's see. So next thing we should talk about is we talk about the area underneath a curve. So when we talk about the area underneath a curve, we talk about area as always positive, right? Always positive. So we have to make the distinction between the integral and the area, right? So an integral of f of x that is above the x-axis is positive, but an integral that is below the x-axis should come out to be negative, right? And so if we're talking about specifically area, we need to break up the interval if our function crosses through the x-axis on our interval, break it up into two different integrals, and evaluate the first one that's above, and then evaluate the second one that's below, and take the opposite of it. If the entire thing is above, great, integrate it, find the area. If the entire thing is below, great, integrate it, and then take the opposite of it, and then you've got the area. But if it crosses through once or multiple times, you got to split it into multiple integrals. Another option, though, is if you do have the, if you are asked for the area, and you're talking about a calculator problem, you can always just use your calculator to integrate the absolute value of the function. So that could occur as well. I forgot to talk about the fundamental theorem of calculus stuff, so I gotta go back and do that in a minute. But in terms of area, that's, I mean, I feel like you guys should be fine with area in the XY plane. Finding area between curves should be easy enough, right? You just integrate f minus g if f is greater than g on your interval. If f is, if g is greater than f, you do g minus f. If it switches between them, then split into two different integrals. If f is above from a to b and g is above from b to c, then do a to b of f minus g plus b to c of g minus f. That should be pretty straightforward. I feel like the area on a polar curve should also be pretty straightforward, but I have noted that a lot of you have forgotten on the quizzes the first time around that we're talking about area of a polar curve, that area is the integral from alpha to beta of 1/2 r squared d theta. And a lot of people are forgetting this 1/2 r squared in there. They're just doing the r, or they might just be doing the r squared and forgetting the half. So don't forget that it's 1/2 r squared d theta. That just comes from the formula for the area of a circle, right? Pi r squared, and then dividing that by 2 pi for the number of radians going around the full circle. Does that make sense to everybody? That's how we got that, right? Pi r squared divided by the fraction of the circle that we're looking at. Okay. That's our 1/2 r squared d theta. So that's your area of the polar curve. What did I say? I said we needed to go back real quick. Everybody's good with the polar curve area. Just don't forget the formula, right? Don't forget the formula. All right, we're going to go back real quick and talk about the fundamental theorem of calculus. So, fundamental theorem of calculus, and this will show up in the multiple choice somewhere, I'm sure, maybe even in the free response, that the derivative of an integral from a constant to x of any function is just that function in terms of x. Everybody good with that? This has to be a constant in the lower limit. This has to just be an x. If I have something like the derivative with respect to x of the integral from a constant to f of, well, we won't call it f of x. We'll put some other function up here. We'll just say x squared of f of t dt. That has to become f of x squared times the derivative of x squared, which obviously we know is 2x, but we have to take f, evaluate it at the upper limit, and then multiply that by the derivative of x squared. Everybody good with that? They might throw something in like, what's the derivative with respect to x of the integral from x squared to x cubed of f of t dt? Well, then that would be f of x cubed times 3x squared, the derivative of x cubed, minus 2x, the derivative of your x squared, f of x squared. Everybody good there? So if you have a function in the lower limit and a function in the upper limit, you've got to do the subtraction because it's a definite integral. Yeah? Everybody good there? The fundamental theorem of calculus stuff. Now, I had a couple kids from AB that were asking me a question about this, and this is something that you guys need to be able to do also in the calculator section. They may give you some problem that you are unable to integrate. Like they may say, what is the integral from 2 to, well, let's see. Well, we'll just say the integral from 2 to 3 of sine x over x dx. Well, they wouldn't do that because that you can just plug in. So let's say, they gave you, now I got to figure out how I want to write this down. Give me half a second. I just had a problem that one of the kids was asking me about. I don't know. We'll just do something like this. Let's say, let's find f of 2 if f prime of x is equal to something like, well, we'll just do something like sine x over x that we can't integrate. And we know that f of 5 is 7. So you need to set this up so that you can use your calculator for it by using the fundamental theorem of calculus. We will say something like the integral from 5 to x of sine t over t dt plus a constant should be equal to f of 5, right? And so, well, should be equal to 7 if x equals 5. And so that allows us to then plug in this 5 up here and say that this whole piece here is 0 plus our constant is 7. So our function f of x is equal to the integral from 5 to x of sine of t over t dt. And if we want to find f of 2, we'll use our calculator to approximate that. And that shows up fairly often in the multiple choice in the calculator section, where you need to use your calculator. You need to set it up using the fundamental theorem of calculus to find that the constant itself is 7 and the lower limit needs to be 5 because those are the values given. And then you can evaluate on your calculator afterwards. Does that make sense? Does that ring a bell to people when we did that earlier this year? I hope. Okay, good. All right. So that was what I want to talk about fundamental theorem. We did area. Just another yes. All right. We should talk about volume. We didn't talk about all of our new techniques for integration. We'll get to that next time. We'll just talk about how to find volume, finding arc length, and then we'll probably call it good for today because we'll probably be done at that point. So 3 different ways that we deal with finding volume. One is volume using cross-sectional areas. And this is sort of two of the different things, but one of them is known cross sections. So we'd say something like base of a solid is, you know, I don't know, sine x from 0 to pi, right? So we'd say the base of our solid is sine x from 0 to pi, and we'd say cross sections perpendicular to the x-axis are, I don't know, we'll just make our lives easier, they are squares, right? And we want to find the volume of this thing. So all we're going to do is we're going to integrate from 0 to pi. And if we sketch this, right, this is what 0 to pi looks like. We have these squares popping out at us. And so what is the area of one of those squares? The area of one of those squares ought to just be the side length squared. And the side length ought to just be sine x. So it should just be the integral from 0 to pi of sine squared x dx. Everybody good with that? Okay. One thing that causes an issue with these sometimes, let's just say we had sine x again, but this time we have semicircles. A lot of times people screw up semicircles, right? Because you think about a semicircle, you draw it in there and you're like, cool, 1/2 pi r squared, right? Well, then people end up saying that the radius, we'll call this thing like sine x, people end up saying that the radius is sine x, but that is not the case. The radius is not sine x, the diameter is sine x. So if they give you semicircles, make sure you end up with 1/2 sine x, or 1/2 of whatever that is. Now, if they gave you quarter circles, because then sometimes I like to do this, is I give people semicircles a bunch of times, and I give you a quarter circle just to screw with you. So if I have quarter circles, then the radius is sine x, right? Because my quarter circle would, you know, I'd have the full thing going around like that. And so the radius is sine x. Does that make sense to everybody? So just be careful when they give you circles. Make sure you sketch it out properly and get the appropriate formula for the area and then integrate it across the entire region. Everybody good there? Okay. Next is solids of revolution. There are two ways to do solids of revolution. I take this thing and I revolve it around the x-axis, let's say, so that we end up with cross sections perpendicular to the x-axis that are circles. And so if our cross sections are circles, then the area of those is pi times the radius squared, where r is the height of the function, just so long as we are fully pushed up against the x-axis when we're revolving around. So if the region is fully pushed up against the axis you're revolving around, and that is the x-axis, your radius should be f of x. And so you just do pi times the integral of your function squared dx integrated from a to b. If we end up with something like this that we're revolving around, right, from A to B, going around the x-axis, as we go around this time, we're going to end up with a circle with a circle cut out of it. We end up with our washers, pi times the outer radius squared minus pi times the inner radius squared. This does not equal pi times r minus r squared. Don't do that. That is not right. And this is incorrect. This is a very common mistake that people make on the AP test. So don't do this. This is bad. Bad. Don't do that. Okay? Everybody good with that being bad? Right? And so you just find your outer radius, you find your inner radius, multiply them, square them both, multiply them by pi, and subtract and integrate. Good? Any questions, any issues there? Okay. of course, we can also do these things around the y-axis. I'm not going to write out a whole bunch stuff of that. Yes, Nick, you can take the pi out, so you can make this pi r squared minus r squared. That's fine too. That's totally fine. That fine. This bad. This all good. What was I going to say? Oh, we can also do these around the y-axis. So if we're going to go around the y-axis, we have to slice horizontally. So we're going to go around the y-axis. You slice horizontally and do everything in terms of y. And note that we don't have to just go around the x-axis or the y-axis. We can go around any horizontal or vertical line that we feel like going around. Just be careful with your radii when you're doing that. Then the other option for finding the volume, which is not required on the AP test, is doing shells. And sometimes shells might make your life a little easier because you might not have to convert to a different variable. But just note that your shells, these are hollow, cylindrical shells, so they, like a toilet paper roll or something, that have a thickness that is perpendicular to the circular way. So the thickness is dx, is the one I've drawn here. And if I were to do it this way, the thickness is dy. Okay. And we just want to do 2 pi times the radius times the height times your dx or your dy and integrate that. And again, the 2 pi can come out. So that's your formula for shells. The chances of you needing shells is 0. The chances of shells making something easier, I would say, is about 1 in 20. I've seen one question in the last 20 years of free response questions where using shells would have made it easier. But I just want you to have it as a tool at your disposal, just in case. Just in case it does seem easier when you're doing the test. Let's see, that's everything with volume. Anybody have any other questions about volume? I mean, there's going to be one area or volume free response question and maybe like a couple of simple ones in the multiple choice. So those of you that are in quarter 1 and 3, we've done a ton of those area volume problems. So quarter 4, they're all up there. There's like 15 or 20 of them. So work on them. And then let's see what else. Last thing for today, I think, is we will quickly talk about the formulas for arc length, I suppose. That seems good. If we want to do arc length, and we're talking about arc length just in the regular xy plane with a regular Cartesian equation, our arc length ought to be the integral from a to b of the square root of 1 plus f prime of x squared dx. Chances are this is going to be an integral that's annoying and irritating to solve. And you will likely have a calculator available to you to solve it. But if they're asking you about like the they could put a fairly simple, they just say like something like x squared or something like that to find the arc length of it. Well, when you do x squared, your derivative is going to be 2x, and 2x squared is 4x squared. You're going to square root of 1 plus 4x squared. That's an integral that you should be able to evaluate using inverse trig substitution, right? 1 plus 4x squared. You should be able to let u equal 2x, and then let u equal tangent theta and deal with it that way. So you might be able to do them by hand, but oftentimes they're integrals that are going to become fairly difficult to deal with on their own. Let's see, if we wanted to do arc length, let's see, still, but we were going to do it with a parametric, let's say, parametric arc length and polar arc length. They're basically the same, right? Parametric and polar arc length. Parametric, we're going to go from T1 to T2, whatever our T values are. And it's just the distance formula, dx dt squared plus dy dt. And then for polar, it's the same, except it's dx d theta and dy d theta. And you're going from alpha to beta, dx d theta and dy d theta. So that should be pretty easy if they give you those to find the arc length. And you can, you can even note that those are, if you think about it in terms of vectors, this is the magnitude, right, of your vector. If you're doing vectors, what else? What else do we have time? We got like 4 minutes left. I think that's probably good for today. Next time, what we will plan on doing is we will talk about the techniques for integration. We'll do quickly U subs, but I'll spend like 10 seconds on that. Then we'll do our inverse trig substitutions. We'll talk about partial fractions. I'm not going to do like reduction formula stuff, but I will mention the integrals that you should just sort of have memorized and know. We'll talk a little bit about improper integrals, a little bit about differential equations, and try and real quickly run through everything we need to know about series one more time. And that ought to cover everything that we've done this year. That first part will probably take about an hour maybe, and then we'll have some time to go over some more stuff afterwards. So what I'm going to do is I'm going to, I will in Google Classroom, I'll just put up the link for the new practice test that I'm going to put up. I am not going to like say what it is. I will just post in the stream the link to it. So actually, I'm not even going to do that. I'm just going to tell you that in the Google Drive, in the assignments folder, there will be an assignment that is titled 2018. That is all it will be called, is just 2018. And my intention for next time, once we get through the rest of this just review, will be for us to go through any questions that you guys might have on those, look at any particular problems in there that might have been a little bit difficult. And then that'll, I'm sure, take the rest of that session. If we have time, if we still need to do more in the last session, we'll do that again and go over any extra free response questions. That last session on that Sunday before the test, I'll also just be available to field any questions you guys might have about anything you've seen and done of the review that's up in the Google Drive over the last couple of weeks since I last saw you. Does that sound good to everybody?